Right. Good morning, everyone. So welcome to the second lecture of our series on Introduction to Quantum Information and its associated technologies, which is the QX01 course of the UTT. So this is the second lecture. So just to give you a brief overview of the program, like we did last time. So next week, there will be no lecture, because this is holidays in France. And the week after that, we will start really on the quantum aspect with the notion of qubit, and then lecture 4 on multiple qubits and entanglement, then measurements and operators, and so on and so forth. So this is the program for today. So today I'm going to cover 5 aspects of what I call classical information and computation. And I will start with a bit of history again, and again it will be very, very short. Then I will talk about how do you actually encode bits, classical bits of information. Then I will talk about transistors as building blocks for our classical information and computation technologies. And we'll talk about gates and circuits, obviously, and then I'll finish with what all of this can give us at the moment. And if we finish before, then perhaps I'll start on the program for the next lecture. Right, so a very brief history of computing, very, very brief. But just to, so here I put up some of the timeline of computers since, well, quite a while. And technically, you could say that the first ones were planetariums, which were sort of orreries moved mechanically with gears, that could mimic the solar system. And in a way, that was the first example of computation, in a way. And then, of course, we have to move along to perhaps early 1940s and Second World War, where really first computers start to kick in. And perhaps one of the most famous one is the ENIAC computer in the 1940s after the Second World War. And of course, late 50s, 60s, 80s, 70s, and so on, the first computers, so the microcomputers, as they were called at the time, first generation, second generation. Then early 80s, the first personal computers, and so on and so forth until, what we have these days, and down to even our phones and watches and so on. And in terms of technology, so I will talk about the technology behind all of this. So there are, like I said, perhaps three major steps. So the first one is the mechanical step. That was, like I said, the first one, of course. Mechanics was always first. It's the easiest you can picture. It's the easiest physics you can picture. And then the first example of a transistor was the so-called vacuum tube. So here I brought two examples of these vacuum tubes. And they were, so here, various vacuum tubes. So actually one of them is a bit more complicated than the others, but roughly the idea was the same. And what's interesting, so I'll just say a quick word on that, because what I find is interesting is that you always have, when you have technology, you always have some history behind and also some physics or math or computing involved, as in steps going one after the other. So the vacuum tube, so just to give you, like I said, I'm not going to give you a full lecture on that, but just to explain where we're coming from. So the vacuum tube was based on a so-called thermionic emission, which is a big word to say that in these tubes, so they were vacuum tubes, and inside there was an anode and a cathode. And so basically you would have a tube like this, you would have one electrode and a second electrode, and this would go to a power supply. And then, so this would be the anode, and this would be the cathode. And the idea was basically to, and all of this was in a vacuum, the idea was basically to heat up the cathode, so that's inside the main tube here, so that you could sort of eject electrons, and electrons would then fly away, hence the name thermionic emission, up to the anode. And so there was more of a diode rather than a transistor. So in a way, that was the first electrical diode. And the idea is that, so it was more to say that you could only have, because physics tells you so, that the electrons can only flow from the cathode to the anode. Is that the electron flow? So perhaps I'll get a. You have to excuse my writing. It's not the best, but I do my best. So the electron flow would be only in one direction, okay? And that's the principle of a diode. And then, of course, again, a lot of technology advances. And by the way, this thermionic emission and this vacuum tube was kind of a useful idea at the time of the photoelectric effect in 1905 or so. So again, to tell you that something that seemed to be very, very fundamental could actually lead to something very useful. And so to finish on that, the second improvement, or one of the many improvements, but the main second improvement was the triad, which is more like the transistor as we know it. And in this case, so it was the same idea. So that's what you have in these tubes. So those are triodes. In fact, one of them is a tetrode, but let's say the same idea. So again, we would find the same two electrodes. So the cathode here and the anode here. Okay, let's get a bit of light here, some colors. And then in between, the idea, so that was in 1907, the first idea came. The idea was to put a grid, a mesh here. So this would be a mesh or grid mesh, metallic, in order to sort of choke the current, to choke the electrons from going from the cathode to the anode. So this was the so I have to close that. So this was the control grid. So let's so something like this. So and everything was well. So this was the control grid. And the idea is that depending on the voltage on that grid, like I said, so you could actually either amplify or choke the current altogether. So you could have no current or amplification of the current. Okay. And using this control grid. So this was the first transistor because basically, as we will see later on, you basically had an outside control, a third control of your electron flow, which is definition of a transistor. So, and you can imagine that all the electronics at the time, so we're talking about before 1940s, before the discovery of transistors using semiconductors, but needless to say that the first computers and first electronics made of those were not exactly small. But again, one thing at a time. And of course, once the transistor came along, so now we're talking about something that is that sort of size, so you probably can't even see it from where you are. And that's even a big one to actually have a demonstration later on. But already you can see a huge improvement between this type of technology and this type of technology. So if we carry on the sort of very brief history of computing, there was also major steps into the architecture of computer. And perhaps the main one was, or one of the main ones was, thanks to John von Neumann, who built or thought of what the architecture of a computer could look like. And actually, to these days, so this is a Pentium 2 on a motherboard, but in all of this and what we have these days is just maybe smaller or more powerful, but the idea remains the same. So you have a CPU, central process unit, where you have a control unit. You need to control everything, everyone. You have a unit that does arithmetic logic, so it's the so-called ALU, that performs the arithmetic and bitwise operations on integer binary numbers. And then you've got to have a memory unit to store information and recover information. So there are all sorts of various memories, random access memories, read-only memories, electrically erasable, programmable read-only memory, and so on and so forth. But you need some form of memory to keep the calculation going. And of course, you need an input and an output that can be given by various connectors or cards you can slide in, and so on and so forth. So this sort of basic architecture that von Neumann came upon with is still pretty much used every day, and to this day into our computers. The idea remains the same. So how do you now, once you have the architecture, so how do you actually encode information? And again, I'm not claiming to give a course on information theory, like done so by Claude Shannon, for instance, and others, because, well, I'm actually incapable of doing so. But what I can tell you is that there is a classical unit of information, of encoding, as you know, which is the bit for binary digit. And why is that? Well, because it's the easiest to do so. To have a binary bit, you need only two states. You need a 0 and a 1. Of course, in the day-to-day life, we use the decimal system. Why is that? Because we have 10 fingers, so probably it's the easiest to code on our fingers. And by the way, there are different ways of coding even on our fingers. For instance, I believe in some countries you do 3 like this, when in some others you do 3 like this. But at the end of the day, if you go down to encoding on 2 states, then there isn't much more you can do in terms of simplicity. And that's good, because you can use elements like this one, or other transistors, semiconductor transistors, in order to have a 0 and a 1. So these two states only. And then from then you need to be able to encode, as I said. So you want to encode numbers, for instance. So here you have 2020, which is quite a memorable year, encoding in bits. So that's what it looks like. So you can see, so you have to have a series of powers of 2s. So 1 2 to the power of 10 plus 1 2 to the power of 9, and so on, up to 0 times 2 to the power of 0, which is 1, and so on. You can have other systems. So we use, as I said, for 2020, this is the decimal system that we use, of course. But we can use binary, or we can use also hexadecimal, or any others, in fact. There are a few that are still in use. And that leads to some form of different calculation you can do, so-called, so for binary, so-called Bool or Boolean algebra. That was developed by George Bool in the 19th century. And you can make, as I said, calculation and operation. So for instance, if we want to know, so we can do that as a nice game. So, how do you encode, how do you find 2020 in binary? So how do you find this string of bits? Well, it's very easy. So perhaps I could erase this part. I mean, there are, everyone has his own way of doing it, but I'll show you. I'll show you one. So you start with 2020, the number 2020, and you divide it by 2. What you get is then 1010, and there is no remainder, right? So remainder 0, remainder 0, because 2020 can be divided by 2. So that provides you the first bit, the 2 to the power of 0, and that gives you 0. And this is what we call the least significant bit, because it's the smallest bit. So the least significant bit, for this number. All right, so we carry on. Then we have 1010 divided by 2. This gives us 505. Remainder is 0. So 2 to the power of 1 is 0. Then we carry on. 505 divided by 2. In this case, you can't without the remainder. So in this case, it gives you 252, if I'm not mistaken. Then you have a remainder 1. Then in this case, for 2 to the power of 2, you actually have a 1, which is the third number starting from the right, 0, 0, 1. And then you carry on, 252 divided by 2. That makes, so 126. Remainder 0, 2 to the power of 3, 0. Then 126, we carry on. That's also we can also divide it, so that's 63. 63. We have remainder 0 in this case, and 10 to the power of 4, 0. 63, this one will have a remainder this time, so 63 divided by 2 gives us 32, which has, with the remainder of 1, so 2 to the power of 5 will be 1. No, sorry, that's 31. 31 divided by 2. So 31 divided by 2 will give us 15 with the remainder 1. 2 to the 6 give us 1. And then we might as well finish now. 15 divided by 2. That's 7. Remainder 1. 2 to the 7 gives 1. Then 7 divided by 2. That gives 3. Remainder 1. 2 to the 8. 1. And then if I finish here, I will eventually get to the most significant bit, which is the last one, which is the, in this case, 2 to the power of 10. Hopefully, I didn't get it wrong. So we are 3. 3 divided by 2 gives me 1. So remainder 1, because 3 is not an even number. So remember 1, how do you put it? Yeah, 2 to the 9. That's also 1. And then 1 divided by 2 gives me actually 0, is actually 0 divided by 2. The remainder is 1. And I've got 2 to the power of 10. I've got 1. And that is, as I said, so this one is the most significant bit, or MSB. In other words, the one that counts the most. And now I can just, pile them up. So I've got 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, 0. So 1, 2, 3, 4, 5, 6. And then 0, 0, 1, 0, 0. All right? So that's a nice operation you can do. And in fact, that's what computers do all the time in order to encode numbers. So like I said, this is a binary system. You can have the same in hexadecimal. So in this case, you only need 3 numbers, which would be 7E4, where in this case, you have, so in hexadecimal, the basis is actually 16. So let me see. Right, so it's 16, so it would be 7 times 16 to the power of 2, because this is bit 0, bit 1, bit 2, like it was here. Bit 0, let's put it in red. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And of course, you can go on and on if your number is bigger. So this one would be only 2, 1, and 0, because in hexadecimal, of course, the base is not 2, but 16. So in this case, you would have 7 plus, E is, I always get it, it goes up to 14. Yes, 14 times 16 to the power of 1, plus 4 times 16 to the power of 0, which is 1. Right? So hexadecimal, you go from 0 to 9, and then afterwards, you do A, B, C, D, E, F to get to 16. Right? So again, so that's one encoding, that's one encoding, that's another one, that's another one. But as we said, so it all boils down to what is the easiest to actually implement. And like I said, well, what seems to be the easiest to implement is the two-state binary encoding. And that's the one that I actually use the most these days. You can also do some operations on these bits. So here is how you find a series, but you can once you've got this series of binary numbers, you can make operations on them. So, for instance, you've got, for that you need a truth table. So you can make all the operation of zeros and ones, which doesn't seem like a complicated thing to do. So for instance, I'll come back, well, you can see here on this slide. So if I have, so if I have, I'll do it like this, I think. So if I have x and y, 2 bits, so I can do so-called a conjunction, which is an AND operation with this sign, so x and y. So the result will be the result of whatever x is and y is, so 0, 0, 0 and 0 gives me 0, 1 and 0 gives me 0, 0 and 1 gives me 0, but 1 and 1 will give me 1. I can also make a not negation, so if 1 is 0, then the negation, the not x would be 1, and 1 would be 0. I can make OR disjunction, so 0, 0 gives me 0, 1, 0 gives me 1, 0, 1 gives me 1, and 1, 1 gives me 1, because it's an OR, so it's one or the other one. So I get, in this case, three ones, and so on. So you have various tables, and perhaps the most famous one for encoding is the there's a mistake here, it should be ASCII. So the ASCII system, which is the American Standard Code for Information Interchange. So here you have a table of all the various encoding possible. So you've got, let's have a look. So here you've got decimal numbers, so from 0, 1, 2, 3, 4, 5, up to 127. You have the binary encoding next to it. So in this case, is all 0, 0, 0, 0. And for 127, you've got 0 and a series of 1, for instance. So this would be in binary. You've got it in octal. We haven't talked about this. So in this case, the base is 8, not 2. You also have hexadecimal here. And you have the actual sign. So let's not talk about those for start, but let's see that from this one onwards, you've got the various signs. So this is the percentage sign, for instance. This is the A sign. Then you start with the numbers, so 0 up to 9. Then more signs, and then you start with letters. So the number 65, which in hexadecimal is 41, gives you the letter capital A. And so on until capital Z. And then more signs, and then you start with the small letters, A, B, C, D, etc., etc. And you have, of course, because you have to do some programming and some encoding, so you have all the first ones which are sort of reserved for special programming. And you have to realize that we're talking also about a radio transmission at the time when this was done. So you've got, for instance, this sign here, which I have a hard time to, but EOT. So EOT is number 4, and EOT is end of transmission, for instance. Okay, or you have also the sync one, which is SRSYN. So that's number 22, I believe. And this one is the symbol for synchronize, when you have to synchronize two signals together. So, and the way you encode ASCII on ASCII bits, you encode on what we call bytes. So 1 byte of information, or 1 octet, is a chain of 8 bits. So here, for instance, you have more than a byte, because you would need 3 up to here. So this would be a byte. of information. Let me find. This is 1 byte because it's 8 bits. Okay. And so this is the so-called Unicode transformation format, the UTF-8 system, which is basically represent 96% or so of what's used in the web right now to encode information. So we're still pretty much down to using these encoding system. So for instance, if I write my name with capital letters, so this would be so the letters in a decimal line. So 67 is capital C. So you find it for Christophe, you find it for my name Couteau. And for instance, you can see that 117, which are underlined, is the U, small u, which is you can find at the end of my name, or you can find it here as well. So this is in decimal encoding in ASCII, and of course, in order to compute that, you want to encode it in bits, so in bytes. So you've got these strings of bytes, each of them representing these symbols, so C, H, I, and so on. And that's what allows us to, to do all these things that we like to spend time on, especially in the last year or so. So this is encoding, and how do you actually implement that? So how do you, so we said you need transistors. You need something that gives you 2 states. So there could be a switch, there could be anything. What we use is transistors. So I talked about the electron tubes, or vacuum tubes that we first used. But of course, what we use nowadays is transistors. So here is one of the first transistors, sort of practical transistors, what we call a bipolar transistor, which is an NPN transistor. So N is tells you that the material that we use is N-doped. Okay, so there is an excess of electrons in that material. And P is it's P-doped, so there is a deficiency of electron in that material. And if you put these semiconductors, 3 semiconductors together, so you form a junction N, P, and N. So N-doping, P-doping, and N-doping. Then you can basically, and if you connect the right circuitry, so this is your central element here, is the transistor. Then you can have this on-off switch, this 1 or 0 state that you need for encoding. All right? So in this case, for bipolar transistor, so there are 3 pins. So it's got to have 3 pins, like the triad earlier. And you have basically a control. So in this case, it's called the base of your transistor. So the base of your transistor will basically control the current flow between the so-called collector C and the emitter E. So I'm not going to give you a lecture on how this works, how the right currents you need, the resistors you need to put in, and so on, because that's not the idea. But pretty much using this type of materials, semiconductors, then you end up with the small component that you can use for your 2 states. So that's the bipolar transistor, but there are different types of transistors. There's another one here, which is called the Mosfet transistor. So Mosfet is for metal oxide semiconductor field effect transistor. So here, in this case, what it uses is to make use of the capacitance effect using an electric field. So here's the here is the symbol for this type of transistor, and of course, in this case, we have to have different names. They are not called base, collector, and emitter, but they are called gate, which is the equivalent of the base, so that's or the equivalent of the grid earlier with the triad. That's what's going to control your transistor state. And you've got on one side the drain, on the other side the source. Okay, so here's what it looks like. So you have again these different doping. So these different materials with different doping, which have more or less electrons to more or less conduct in one side or the other. So here you've got n-dope elements. And you can see that these n-dope elements, in between them there's a p-dope element, a p-dope material. And that's what stop the current flow going from this component to this component. But so that would be the source, that would be the drain. But using this gate, so using a top electrode and a bottom electrode, if you actually apply a strong enough electric field, you will be able to bring electrons up to the gate electrode, and they will be stopped because in between the gate and the rest of the substrate there is a thin layer of oxide, so a thin layer of insulator that will prevent the electrons to actually reach the metal. And if you remember the first lecture, I told you that nowadays typically these dimensions are getting so small, so on the orders of few nanometers, 5 to 10 nanometers, that we have huge problems because thanks to quantum tunneling, electrons can actually hop through this supposedly insulating layer. But okay, let's say in these cases it's thick enough so they don't go through, so they get stuck here. But at some point there is an accumulation of the electrons just at the interface here, and this accumulation of electrons will make to make it simple, will sort of n-dope now this formerly p-dope substrate just at the interface, and you basically will create a channel between the source and the drain that will allow the current to flow, electrons to flow. So that's perhaps the two most famous transistors, and there are various types of transistors. So here I put you there are basically three families, so the bipolar transistors and the field effect transistor I just talked about. You've got some sort of mix in between, and then for each of them you have different families. So the FET, I talked about the Mosfet, there is the JFET, the FinFET, and so on and so forth. And what's interesting is that for each of those, of course, we haven't talked about it so much, and we won't talk about it too much, but you understand that there are some material science involved as well. So you can see here on the left-hand side all the various materials you can use in order to make these various components, whether they are bipolar transistors or FET transistors. So you can see different materials, so silicon, of course, but also silicon carbide, or SOI, which is silicon on insulator, which is used a lot. Also gallium nitride for some applications, for some specific transistors. So here you have a piece of silicon. So it's a silicon crystal that has been grown like this, and then it's been sliced. You can see how it's been sliced in thin, what we call substrate, so thin or wafers. In this case, is about a 2-inch wafer. And I will basically give you the basics for your transistors, so the basic material. It could be, for instance, this P substrate, because of course, why we use these materials, silicon especially, is because you can dope them, you can dope it at will, N-type, P-type, N plus type or N plus plus if you want to extra dope it, and so on and so forth. And with this starting point, so you start from rocks also, so you end up with the single crystals, and eventually you end up with something like this. So you probably can't see, but in here, this wafer, so this is a silicon wafer, so rather big. On this silicon wafer, they are engraving, they are sort of junctions and connections and so on, and various etching that have been done in order to realize such structures with electrodes on top, electrodes at the bottom, and then structuration with the oxide layer and so on and so forth. So you probably can't see it, but you may be able to see the various colors, which are due to the fact that you have various materials on top, like the metal, oxide, and then the rest of the semiconductor, silicon semiconductor. And just a quick word on that also, because when you talk about material science and materials available, you have to talk about abundance and potential pollution of some of those. So this is, again, I'm not going to give you a course on this case material science, but this is something that we also have to keep in mind, that some of these materials, some of those elements are actually getting diminished, and we have less and less of them to deal with. So this is something for future technologies, perhaps for future quantum technologies, to keep in mind as well. Right, so once you've got all these elements, then before, maybe I thought I'd show you. So before, let me get back to the transistor before I go into gates. So what you have here, so you probably can't see very much, but I'll explain what we have. So those are not useful. So in here, you've got a transistor, so one of those that I put in with the 3-pin. So on this circuit board. And I'll show you what the electrical connection is. So I use this, so this was used, it's not used much anymore, but it's the so-called logic trainer. So it's quite nice, I quite like it actually. Because you will see afterwards that, so now I'm going to show you a transistor effect on that, on one transistor. But after I'll show you how with this guy you can also make various gates like AND gate or NAND, NOR, and so on. So it's pretty cool. Right, so so I won't get it wrong. So the electrical circuit that is here looks like this. So we've got the central element, which is our NPN bipolar transistor. So we've got the base here. We've got the emitter here, the E. So wrong one. Let me show you the right one. Okay, so here's the collector, here's the emitter, here's the base. And then we've got a resistor. I'll use the sort of Anglo-Saxon conventions. You've got a resistor of 330 ohms. And this is powered to a 5 volts power supply. So in here, I'll show you after. And in here, so there is basically an LED that will give us the state of the transistor. Okay, that would be this one, number 5. Yeah, this one. So for now, everything's off. The emitter is linked to the ground. Then at the base, we've got another resistor, which is going to be, in this case, R2 equals 1 kilo ohm. And then this is linked to inside the circuit board, so that's why I'll represent it differently, but is linked to another resistor that I don't know how much it is, but doesn't matter. And it's powered, and then there's an interrupter, a switch. Interrupter is interrupteur in French, so that would be switch. So there's a switch that we can flip on and off, and that will change the state of the transistor. So this is actually inside the box. I'll show you afterwards. And the switch is called P2 on this box. And then here, sorry, I said I would use UK convention, so let's use same convention. And here you've got another resistor, and then you've got another LED. Which is red LED, and this one is also red. And it's number 5, and I say that, but it's because it's the one that is here. The one that is here, the red one, is this one. And this one basically tells you the state of the switch. So when this one is on, the switch is on. When this one is off, the switch is off. Okay? So here's what I have here. So I've got the transistor is here. I've got the three resistors. So I didn't put this one. Is also R1, same one. I've got 2 R1s and 1 R2, so they're here. This is linked to, oops, it's gone off, to P2. Here we go, that I just plugged. So P2 is this part, which contains the switch, which is here. Okay, that I can flip. And I think that's it. And for some, in this particular case, so when I'm going to flip that on, the switch will be off. So when the switch, so the switch I will call P2, switch, let's try to write it a bit better than this. Switch P2 is on, then the transistor is on the 0 state. Okay, it's inverted. When P2 is off, so open, and that's the switch, then the transistor is on the 1 state. And that's where this light, so so 5, so LED 5 is on. Okay, it's the other way around that what you would think, but it doesn't matter. I have to, this one, okay, voilà. Oops. It's quite old technology, but it will work at the end. So forget about this one for now. Just look at this one. So, oops, there we go. So the LED, the red LED number 5 is currently on and is lighting when here, this one. Oops. Voilà. So, and P2 and P2 is off. So the transistor is in a so-called one state. Oh, I've got some issues here. Now, if I flip the P2 switch, then in this case, 5 is off. And you can see, yep, here we go. Well, you probably can't see, but this LED here is on. So when this LED is on, then I mean P2, the switch is on. Okay, that is in the good, I mean, the expected way. So when this LED, which is this one here, is on, the switch is on. Okay, so here the switch is on. The LED is not red, the switch is off. But in this case, I've changed the state, the transistor is on, is in the one state. Okay, could be the other way, but it doesn't matter, it's the same idea. Switch on, transistor in the 0 state, switch off, transistor in the 1 state. Okay? So, but the point is that, so you can see that, you know, all of this, I mean, seems rather complicated, but at the end, it's not. I mean, of course, here is a bit more complicated because we've got LEDs to show the transistor behavior, but in real life, we wouldn't have these LEDs. We only need some power supply, 5 volts, maybe 12 volts, maybe 7 volts, depends on the transistors, but say 5 volts, and then some resistors that you put in, the base, and collector, and emitter. And at the end, you've got a transistor. And all you need to do now is just to take that and duplicate many times, and to actually you know, bring down to very small dimensions, and not just like that, in order to make more complicated calculations. So what are these more complicated calculations? Well, there are these gates we talked about. And why is that? You will see. So in Boolean algebra, you can construct various gates. And for that, you need what we call truth table. So here I give you some of the classical gates that are used in binary logic. So, of course, you have the one that is, well, not useless, but not far from it, which is the yes, which is basically you don't do anything. So an electrical wire is a good gate for that. But the one that is useful, or could be useful, is the NOT gate, the one I talked about. So if you have an input state 0, then after that element you got a 1. And if you have an input state 1, then after that element you get a 0. You can have gates, you can put together operations between bits. So you've got the AND gate or the OR gate. So those three are actually what we call the primary operations, because with them you can make up the others. So the AND gate we talked about earlier, and the OR gate as well. So here are the symbols. So 0, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, 1, and so on. You can make an XOR, so it's an exclusive OR. So it's the same as the OR gate, except that you want to be exclusive, so that means the 1, 1 is actually 0, so the truth table is not 0, 1, 1, 1, but 0, 1, 1, 0. You can have a NOND gate, which is a non-AND gate, so the opposite of an AND, so you got 1, 1, 1, 0. You can have an OR, so it's the opposite of an OR, or an XNOR, which is an opposite of an XOR. Okay? And you can make basic operations, basic calculations. So these are a way of writing it. So for instance, in Boolean expression, when you have Z, so the end of between A and B of 2 bits A and B is Z would be A times B. Here would be a NAND, so you put a line on top. This would be an OR, which is like a sum, basically, and so on and so forth. Okay. And what's interesting, of course, is that out of these, so for instance, in order to construct an XOR gate, you can actually construct an XOR gate out of these three I mentioned, well, out of some of the other gates. So in this case, you need one OR, one AND, and one NAND. Okay. So we can try that. Let's see. So let's try to see whether, indeed, using the basic operation, then whether this XOR can be made up with those. So using the truth table of the NAND, the OR, and the AND. So let's try that as a small exercise. Maybe I can erase here. This time I'll try not to go off the screen. That would be nice. So the first thing is you take A and B. Oops, sorry. You take A and B, and you send A and B to a NOR gate. So this is a NOR gate. So I can write that. So I've got so a truth table. Okay. So that's 0, 0. Well, 0, 0, 1. That will give me a 1. 1, 0 will give me a 1. And 1, 1 will give me 0 because it's the opposite of an AND gate. Okay. So that's one side of the operation. So this one. Then if I look at this one, which is an OR gate, so this is a truth table. I just need to rewrite this. So an OR gate would be something like this. So 0, 0, 0, 1, 1, 0, 1, 1. Which is, in this case, oh yeah, sorry, my mistake, my bad. Because in fact, what you want for the OR gate, you want, yes, no, that's right, you want A and B, so that's right. So the OR gate, I just need to write it, so that's 0, 1, 1, 1, in this case. So 0, 1, 1, 1. Okay, so now I've got NOR and the OR, and I need to put the two output of those together. So this one and this one. So if I do that, so that would give me third truth table. So NAND and OR. So the NAND and the OR are actually the two output now of those. So here and here. So it could be C and D. Say, let's call it. So this is result C and this is result D. So this is C and this is D. So it would be 1, 1, 1, 0, and then it would be 0, 1, 1, 1. And I make an AND gate out of C and D. So AND gate means that I would get 0, 1, 1, and 0. Okay? And this is indeed the result that we have for, where is it? An XOR here. Okay? There you go. So, there you go. So you can see by sort of very simple calculations using these very simple gates, so one bit gate or two bit gates, that you can well, make up all different gates. Of course, I guess you could see that coming because we will talk about the equivalent in the quantum technology aspect, where we'll talk about single qubit gate and 2 qubit gates. And we will have the equivalent of that, although not quite, as you will see next time. So from that, so for instance, if you take 2 transistors, like so, like these ones, you can make an AND gate. So an AND gate is actually a multiplication of two numbers. And here you have an example of what we call a 4-bit binary adder. So it's basically a circuit that will sum 2 4-bit numbers, 4 binary bit numbers. So you can see, again, we have a NON here, we've got XOR, AND, OR, and so on and so forth. And by combining all of this, you get basically the sum of these 4-bit numbers. So it's A1, A2, A3, A4, sum with B1, B2, B3, B4. Okay, so you have 2 4-bit numbers, and you want to sum them up for making a simple calculation. So that's what you need. Okay, so you need all of those gates. All of those gates, so each of them can be made through, thanks to these transistors. So here's just one example of 2 transistors to make an AND gate. But using a clever way of putting these transistors together, you can make any of these other gates. So the, sorry, it doesn't always work this, but never mind. You can make the XOR or NON and so on and so forth. Okay. Right. Oh yeah. So I thought I could show you. So here. So for instance, in here the. I have to not make sure. Yeah. Here we go. Well. So now if I look at the number 7, so the number 7 here is actually linked to a NOT gate. And number 7 is basically the complementary of the red LED here. If you remember, I told you that this red LED gives us the state of the switch. So when the red LED, this one, is on, then the switch is on. And then after that, this is linked to a NOT gate, which is inside here, this one here. Oops, if it's not plugged in, it's not going to work. Here we go. So now if I change the state of P2, then this is the outcome. So number 7, I told you not to look at earlier, but now you can, because this gives us the opposite state of this. So when the switch is off, this is not lighting, but this is, because it's the opposite state of the switch. So when the switch is 1, this LED is off. Okay, on, off, off, on. Okay. You also have an example here between, so I've got the switch, so these 2 switches, so P0 and P1, these 2, are linked to an AND gate. So now you have to look at this one here. I can switch that one, voila. Number 6. So number 6 is basically the output of an AND gate. So this one, okay, or do I have it here? No, I don't have it here. Or this one. And you can see, so this one will be 0, 0, 0, unless the 2 switches are on at the same time. So let's see, right now the two switches are off, so the LED is off. One is on, LED is still off. The other one is on, LED is still off. and then the 2 are on. This one is on this time. Okay, so this circuit here with 2 input and 1 output is just a simple AND gate. And so with this sort of nice logic trainer, you can see you have different NOR, NAND, OR, AND gate, and so on. You can actually play around and make more complicated structures like this one, or perhaps even this one. And at the end, once you crammed all of those transistors into all of these gates, then you cram that into integrated circuits. And that was also one of the major breakthrough from the 60s, 70s. And from then, well, you've got the complete chain of information, basically. You can go from your transistor, your basic components with your 0 and 1, up to your logic circuitry, where you have truth table like this. Then you go up to integrated circuits. Eventually, you go on to motherboards, like this guy. Then that makes up computers, and then you can link up that to the world, and you can link it up in a fast way now with optical fibers. So here, don't know about you, but in France, not everyone has fiber, unfortunately. I am very lucky, I got it recently. And this is exactly one of the fibers I have in my home, so plugged into my provider box, and this is on the wall. I can just, plug it in here. There we go, and so this would be plugged to the wall, up to the street, and this would be plugged to my whatever provider box for the internet, Wi-Fi, Netflix, and whatnot that you have at the end. Okay. Right. So so I think on this part, that's what I wanted to say. Again, the idea is before we talk about the quantum world with all these sort of superpowers, you need to know where we start from. Okay, so of course, again, this is what in less than an hour, perhaps I gave you, and also what my view on classical information and communication technology. But it's just to have a very brief and quick brush up onto the so-called classical world, in order to understand how different, how more powerful the quantum world will be. Okay, so that was it for this part. As we have some time, which is good, then I can introduce some of the topics for next lecture, which is on the qubit. So now you can see, so the first thing I will do is I will try to show you what is the fundamental difference between bits and quantum bits. And we already talked about the first lecture, but here I will insist on that, and it's more to the point. We will have to go into the mathematical representation of quantum bits, and that's where things will start to get a bit nastier. If we talk about quantum bits, so probably not today, but for lecture 3, when I'll actually go back into that more properly, you have one useful representation is the so-called block sphere representation of qubits. So I'll show you that. How sort of 3D representation you can basically make up any orientation, any state of a qubit. And I will finish, again, next lecture, not today. And today I will talk about 3.1 and perhaps 3.2. And I will give you an example of a simple qubit, or at least what what I consider a simple qubit, which is a photon. So, like I said in the first lecture, there are, and we will see some of the technologies, not all of them, some of the physical implementation. I talked about some of them. I will talk about some others and other technologies associated to it, but not insist too much. Although what we will do during these lectures is use the photon, so a single particle of light, has the sort of model of a qubit. And you will see why, because using the polarization state of a photon is actually sort of fairly easy to represent a qubit that way, or at least on paper. Right. So let's start. So bits versus quantum bits. So bits of information, we talked about it. A bit of information is a two-state element of a 0 and a 1. So a quantum bit is also a two-state element of a 0 and a 1. So like I said, in some physical implementation, it could be the polarization state of light, or it could be the quantum spin of an electron, or any other things. But the fact is, it's got also to have two states. So that we keep from the binary system is we keep only two states. So to the bit, we have the 0 and the 1. And to the quantum bit, which we call for short qubit, so we write it like this. Sometimes you can see also the notation like this, which I personally do not use, but it is used as well. It's fine, I mean, whatever, it's just notation. And in this case, we also have the two states, 0 and 1. So of course, we need to differentiate our classical bit from a quantum bit. And for that, we will use this, and I'll come back to that later stage more specifically. In fact, the next lecture and the lecture after that. We use this sort of weird notation, which we call the Dirac notation. So this, so ... is 0 or 1 or other things you will see. We can put more things. We can put, for instance, 0, 0 for a two-state qubit, or even 1, 1, 1, 1, and so on and so forth. This is called the Dirac notation. From Paul Dirac. And you will see that this is not just a notation. All right? There is, I mean, it's a very, very practical, ingenious representation. But it's not just a representation in the sense that behind this there is a lot of physics going on. We won't see all of it because, again, this is not a lecture, this is not a series of lectures on quantum physics. But we will touch upon the physical aspect of the so-called Dirac notation, or the bracket notation, because you've got a bracket here. And in fact, what there is here, what this part is not a bracket. We don't call it a bracket, but sorry, let's say here. This, we call it a ket, so half of the word bracket. And the bra part, so this part, will be seen later on. Okay, so this part will be seen later on and will look like the counterpart. And when you put these two together, you form a bracket. Right? When you put this one and this one together, when you have the bra and the ket, you form what we call so a bracket, which we usually write like this with, say, a 0 and a 1. But just forget that for now. Let's concentrate on this, all right? This notation. So you have two states, 0 and 1, with this sort of weird notation of bracket system, Dirac notation. Okay, so nothing new here. We got the 0 and we change the way of representing it, and so what? Well, now our qubit, which we will call psi, again with this representation of bracket notation here. This qubit is actually not, the output of a qubit is not just 1 or 0, as opposed to a transistor, as opposed to one of these guys, which has either a current going out or no current going out. But quantum physics tells you that you can have something in a superposition state, okay? Something that is in two states at the same time. If you remember what I told you, quantum mechanics tells you that if I run against a wall, I have a non-zero probability to go through the wall. In fact, quantum physics tells you that at some point, I can be seen as in a superposition between being on one side of this wall or being on the other side of this wall. Again, for me, it doesn't apply. It wouldn't work. But for an electron or a photon, so a single particle element, under the right conditions, you can have that. You can have this particle. So I talked about quantum tunneling. So you could have an electron that is in a superposition state between being on one side of this insulating layer or being on the other side of this insulating layer. And in fact, the electron, at some point, you do not know where it is. So in fact, in essence, the electron is in both ways, on one side and on the other. So it's in a superposition of both. Okay, it's in the two places at the same time. Okay, and that's what a quantum bit is that you take the two states and you put it in a superposition with some coefficient, so some weight, alpha and beta, of 0 plus 1. Okay? And so your qubit, as opposed to your bit, which is just a switch, you can see your qubit as being like a tunable way. So you have this way of tuning the weight of alpha and beta. So of course, you can tune all the way down. You can dial from one side up to the other side, meaning that if you dial to one side, you can have beta equals 0, then therefore psi is in the 0 state, or you can dial on the other side and have alpha equals 0, so that phi is in a 1 state, like the classical case. But of course, what's interesting is when both alpha and beta are not 0, when you can dial somewhere in between. Okay? Because then you end up with being in that sort of superposition state of being both at the same time in a 0 state or in the 1 state. So the equivalent of this passing or non-passing through your transistor, through your quantum transistor in a way. Okay. So, all right. So that's something. So for practical applications, we like, but it's not a big deal for now. But we like to have normalization of state. So in a sense that we like to have 1 or 0 at the end, or between 1 and 0. So that means that when you dial up from alpha to beta, those have to be, so if alpha equals 0, then that means beta equals 1. And if beta equals 0, then alpha equals 1. And you have to have alpha, the psi quantum bit in terms of amplitude between 0 and 1. So we say that it has to be normalized. And I will show you just straight after the mathematical analogous of a quantum bit, which can be seen as a vector. Okay, a vector with a basis 0 and 1 with 2 states. And a vector, you can have normalized vectors. So in a way, here is what we have. So this qubit has to be normalized to 1. That means that there is a relation between alpha and beta, these two coefficients, which is that alpha squared plus beta squared equal 1. Okay? But that's not it, because as you can see, I'm using complex notation, because those coefficients, in the most general way, so alpha and beta, in fact, is not, it's not here. Oh, yeah, it is down here. They are complex numbers. Okay, so that's another sort of major difference with classical information and classical bits, is that in the quantum world, we live in some special space we will talk about later. In quantum physics world, there's some special mathematical space where we live in that allows for complex numbers, that allows for complex mathematical quantities to be used. Of course, at the end always, you will see in physics when we say you make a measurement, so you want to know what is the state of your system, you don't see a complex number, you see a real number. But let's forget for now. Let's forget this for now. Let's just say that we allow alpha and beta to be complex numbers. Okay? So this is a qubit. In case you've never seen one in your life, then this is it. So this is the most basic element of information for quantum information technology, for QIT, where you have this superposition of 0 and 1 with these two coefficients, alpha and beta, that you can change at will. And you have normalization aspect to take care of as well. We don't have to. I mean, normalization aspects, actually, you don't have to do that. But it's like in math, when you usually when you talk about unit vectors or sort of basis or basic vectors, you like to have unit length of these vectors. So in a way, it's the same idea here. Right. So now you can say, okay, well, this is very well. I've got this quantum state. So all right, it's a superposition of being left and right, or 1 and 0, and so on. It's not very clear to me what it is. Fine. Then in this case, you can say, all right, let's just do some math here. Let's not worry about the physics out of it. So, all right, so let's find an analogy to our quantum bit. And the analogy of that can be seen as a vector, a two-dimensional vector, where you have two vectors. So this is a vector, and this would be the basis in 2D dimension. So vectors, okay, well, we know that. In 2 dimension, x, y, say, you're in 2D space. So that's easy. Okay. So 2D space. X, y. Got the 0 here. And you've got the basis vectors. So I call them, how do I call them? Ex and Ey. Here. So these vectors are normalized. Usually, we like to use them. So the norm of these vectors is 1. And I can represent a vector, psi, right, in this plane by saying that, you know, this vector is basically alpha. I've got to move this direction from alpha quantity, and I've got to move this direction by a beta quantity. So there we go. All right. So, okay, so how about I call this like this, and how about I call this my 0 and this my 1? But those are just notations. Okay? Like I said, they're a bit more than notations. But for now, we can just say they are just notations, which they are. Right? So, and then you've got we have our coefficients, alpha and beta, except that in this sort of standard 2D space, this is real, in the real space, the coefficient alpha and beta would be real, or not here. For a qubit, they're not real. They're complex. Okay. Oh, sorry. Okay. And yeah, so another, like I wrote here, I mean, another notation, it could be, again, these are just notations, so I could write it like this. Be the same way, 2D vectors. So you can see that by this representation, then this notion of superposition is not a big deal, right? Because you have this vector, and you can go from 0, so the state 0 here, along Ex, if beta equals 0, up to along Ey, up to 1, if beta equals, if alpha equals 0. And anything in between is possible in a real space, with alpha and beta being some numbers, negative, positive, whichever. Another way of representing them, so I put that here because we will use that later on. But in vector notations, as you know, we can also write for 2D, so if I take this notation, we can also write it, say, being a vector column 1, 0 plus beta vector column 0, 1. Well, 1 is for, or if I can write it like this, for Ex, and 0, 1 would be Ey. So you will see that the notion of a vector column is very important because we will see the idea of vector line. Okay, and in fact, the vector column. So this is vector column notation. Vector column. Oops. 1, 2, 3, yeah, that's fine. Vector column notation. So this would be for the kets we talked about. And you remember I talked about this sort of opposite ket, which we call a bra. And in this case, I will show you next time, these bras will be vector lines and not vector columns. Okay. So just as a preview, so these bra vectors will be, vector lines. Oops, starting to be tired. But let's set that aside for now. So vector lines are something like this. Sorry. So something like this. But let's see that. Let's keep that aside for now. All right. So, okay. So we've got this analogy between our qubits. So something like this. And vectors. Right? Knowing that, again, is an analogy, is not strictly equal. Because for the reasons I said, for instance, the coefficients are complex numbers. Plus the rules are different, like the counterpart, for instance, of the bra operation. But it gives us the analogy. So by analogy, we have also operations that you can make on these standard vectors. So you can have a rotation matrix. Okay, so if I take this vector and I multiply it by a rotation matrix, that would look like that. So this is the most general matrix you can think of. You can rotate this vector, and you will obtain another vector. So, you know, if you take, so here's the rotation matrix that we use in standard geometry. And I can obtain, so if I apply this rotation matrix to my original vector, then I get another vector, which is a rotated vector psi prime. Well, we will see that we can do the same with our qubits. So we can apply rotations or gates or operations, which will be also matrices, to our vector, to our qubit. And we end up with another qubit, psi prime. Okay? So this would be the okay, so I start from this qubit. I do an operation on it, so it could be, so I call it A. It could be a rotation, it could be a gate. We will see examples of them, like the Hadamard gate or the non-gate, equivalent of the ones that we had classically, we just saw today. And I end up with a different qubit, like I end up with a different vector here. Okay. So this quantity here is a 2D matrix. Okay. And a few things to say about it. First of all, we like to put a little hat on top. We don't have to, but we like to put a little hat on top. And again, this is in order to this is more, the significance is more in physics again, where we want, usually these operations are linked to actual measurement that you can make. So in physics, a measurement is what? Is you measure a current, you measure the spin of an electron, you measure the polarization state of a photon, you make a measurement, okay? You take an apparatus, you make a measurement. And the fact that you come with this apparatus and make this measurement, in physics, this is what we call an observable. So it's something that we physically observe. This is something we don't live in the quantum world. We actually live, as in you and me, we live in the real world where we make observations, where we make measurements. And when we talk about observables, then these are equivalent to this sort of operation that you can do on your qubits, and for that we put a little hat on top to show that there is a physical meaning to it. Okay, you actually do something. You use some measuring device. So that's the first difference. The second difference is that these matrices, unlike the rotation matrix, they can be complex. Okay, I mean they can have complex numbers. And in fact, they have particular rules. Okay, they are what we call Hermitian matrices. From Hermit. But we'll get back to that. Hermitian matrix. Sounds rather complex, but it's just matrix with different rules, okay, as we will see. So those are examples of these Hermitian matrices. You've got 4 of them here. So this is a 2x2 matrix because, well, our qubit is equivalent to a 2D vector. So therefore, our matrices are 2x2 matrices. And what you see here, so these 4 matrices, so sigma 1, sigma 2, sigma 3, and the identity matrix, where there is a mistake there actually. Those actually, you can show that these, so we call them the Pauli matrices from the physicist Pauli. And you will see later on that those play a significant role. They are very important in quantum information and quantum computation, okay? Because those matrices are actually gates that are used quite a lot. But again, for now, let's forget that. I just want to highlight these matrices. So sigma 1, sigma 2, sigma 3, and identity. Alors, be careful, there is a mistake for the identity. So I shall write it here. So usually we write the identity matrix like this, again with the hat, and so I rewrite it because it's a mistake. Is this, so there's not a 1 here, this is a mistake. And the others, so sigma 1, those don't have the hat, but we can put the hat. Sigma 1, sigma 2, sigma 3, so those are the Pauli matrices, okay? And the fact that they are important is because these matrices, so in 2 dimensions, you can show that any 2D matrix A, so one of those, so any, or in physical terms, any observable in physics in 2D state, which is the case here we're interested in, can be written as the superposition of those 4 matrices. Okay, so those four matrices, so the three Pauli matrices plus identity, they actually form a basis for all 2D matrices, emission matrices, observables that you can have in quantum information. So it's important to keep that in mind. And finally, and I think I will stop on that. So I told you that Hermitian matrices are just matrices, but a bit different. They're different because they have to follow a specific rule. And the rule is that a Hermitian matrix, A, has to be equal to the so-called A dagger, so it's itself, but with an operation that we call dagger. Now you can see here, there's this sort of small, or sometimes people say cross, A cross. I use A dagger, hence perhaps due to my last name, but it also looks like a dagger. And the dagger operation is a bit particular. It's not something that we usually learn when we learn matrices or matrix algebra at first. So I'm not going to do some examples today, but I will next time. Again, also I'm not using these matrices, but I will next time. This was, again, more like a preview for the next lecture. So those matrices, they have to follow, so they have to be equal to their counterpart, which is A dagger. So this is called dagger, or sometimes cross. And what is the dagger operation? Dagger operation is that you take, first of all, you take the complex conjugate of the coefficient of the matrix, and then you take the transposed of the matrix. This is the, so, yeah. So dagger is conjugate plus transpose, okay? So for instance, if I take A equals, well, let's say, let's take sigma 1, sigma 2. Yeah, let's take sigma 2. So sigma 2. Sigma 2 is 0, I. I told you complex numbers. So if I take the complex conjugate of that, I have minus I and plus I. And now if I take the transpose of that, which is sort of the reversed mirror operation along the diagonal, then it simply means I invert these two coefficients. I end up with 0I minus I0. And that is precisely sigma 2. So sigma 2 and sigma 2 dagger are equal, which means that this is an Hermitian matrix, which is good. Hermitian equals good for now, okay? Remember that. Right. Okay, so I think I'll stop here for now, for today. And so the next lecture, which is not next week, in 2 weeks' time, so I will come back to that part and go further and also apply some of these calculations to simple qubits operation. And that will lead to single qubit operations, so single qubit definition, single qubit operation. And that will lead us to then multiple qubits, and then the very important notion of entanglement that we talked about already in the first lecture, and eventually to gates and so on and so forth. And we also have at some point to introduce, well, it's gone now, but like I said, the bra notation with the idea of the vector line, not just the vector column, but the vector line representation that we will need later on. And with this, I thank you for your attention, and I'll see you in 2 weeks' time. Thank you.